at the Matrix AI Seminar Series. We have a young research scientist joining us today from Vanderbilt University, Nashville, Dr. Soheil Kolouri, who is an assistant professor at computer science and also the director of Machine Intelligence and Neural Technologies Lab. His interests are in continual learning, geometric deep learning, and computational optimal transport. Prior to joining Vanderbilt, he has done some broad and large DARPA programs as a research scientist and PI at Hughes Research Labs, Malibu, California. He obtained his PhD in biomedical engineering from CMU, where he also received the Bertucci Fellowship Award for Outstanding Graduate Students and also the Outstanding Dissertation Award from the Biomedical Engineering Department. And I had a pleasure of working with him on lifelong learning machines. And I'm really looking forward to your talk, Soheil. The floor is yours.
Thank you so much, Tarisha, for the kind introduction and for the invitation. It's a pleasure to be here today and presenting some of my recent work on continual learning to you all. So machine learning has become a disruptive technology. One of the reasons you are all here today is because we're all interested in machine learning and how it's affecting and influencing all industrial and scientific sectors. So for instance, in healthcare, we have commercially available machine learning solutions for detecting diabetic retinopathy or for performing augmented reality microscopes with real-time detection of potentially cancerous regions and so on. In transportation, fully autonomous cars have become a reality, although they may not be as safe as we want them to be yet, but we have them. And in the energy sector, machine learning is contributing to smart grids and predictive modeling of renewable energy and so on. But although that the field is moving rapidly, today we face many challenges. Specifically, when it comes to deployment of machine learning approaches and particularly deep learning models, we face some serious challenges. So here are 4 roadblocks that my lab, among other research labs, is actively working on. We have data and label efficiency issues with our deep learning models today. We know that our models are very data hungry, and these models used to be very label hungry, and they are arguably very label hungry today as well. But with the advances in self-supervised learning and semi-supervised learning approaches, this label efficiency issue is diminishing. So now we really need to focus on having more data efficient deep learning algorithms. So that's roadblock 1. Roadblock 2, as we see it, is explainability, which of course, is a major challenge with today's deep neural networks. They're often treated as black boxes. And although there has been a lot of recent research on explainability of these models, this remains an active field of research. And explainability is very important because unexplainable models reduce trust in applications where we have human in the loop. And they also hinder scientific discovery. So if you would like to use machine learning for scientific discovery, we really would like to have explainable models. The third challenge is robustness to natural or synthesized adversarial examples. So this is a famous figure from Ian Goodfellow's paper on adversarial attacks, where a network correctly classifies an image as a panda with like some 57% accuracy, and then with a small unperceptible added noise, the network is completely fooled, and it just says it's a gibbon with 99% accuracy, right? So in general, robustness to out-of-distribution and performing out-of-distribution detection remains a major challenge in today's deep learning approaches. And lastly, we have continual lifelong or incremental learning as a major challenge in machine learning. So I'm going to be mainly talking about continual learning today, but I just wanted to mention that there are also other challenges in today's deep learning, including, but not limited to, embodiment, causal inference, common sense reasoning, and fairness. Okay, so these are all very important challenges that make it very exciting to work in the field of machine learning. Okay, but I would like to start by motivating why we are interested in continual learning. We all hear a lot about success stories and advances in machine learning. For instance, deep learning was successfully used in detection of diabetic retinopathy, as I mentioned, and also has been used for classification of skin cancer. These are two sample papers that show these results. And the claim in this type of works is that the AI system achieves expert level or better than expert level performance on specific problems. So this is really exciting, right? We have machines that can do better than experts for these particular tasks. But on the other hand, we also hear a lot of failure stories, specifically in critical applications like healthcare and autonomous driving. And this could be really confusing, right? Whether machine learning works or it doesn't. So which one is it? But if we go back to the fundamentals, we see that there's a core assumption in machine learning that the train and test samples must be independent and identically distributed samples from a stationary underlying distribution, right? So that's the core classic assumption in machine learning. And it turns out that in our success stories, human experts and the machines are evaluated under the setting that this assumption holds. So this IID assumption, if not perfectly, it's closely is relevant to the application. But the failure stories are often caused when this assumption is violated, when we have a very different distribution or training than or test time. And of course, because this fundamental assumption is violated, we should not expect our machines to perform very well. So all that to say that there is still a huge gap between human performance when it comes to out-of-distribution scenarios, and humans are able to generalize to out-of-distribution scenarios, while our AI today remains far from that. So, and by the way, please feel free to stop me and ask questions, and then we will also have like question time at the end of the talk. But if there is a question that you would like to ask, please feel free to stop me. Okay, so as we said, the main assumption in classic machine learning is that the data is generated from a stationary distribution. And we know that real world does not agree with this assumption. We have continual shifts of the distributions that we need to, the distribution that the data is coming from, and we need to train our models on. So here we are looking at the seasonal changes and medical applications, the variations among imaging devices, for example, or the variations in computational imaging techniques that are used to generate medical images could result in shifts in the distribution of the data. And now our models need to adapt to these shifts. And we all coped with COVID in the past few years, so we know how fast the variants of a disease can emerge. And these new variants could change and shift the distribution of the data that we are observing in medical domain. So we see that we need to be able to cope with these shifts in the distribution, and continual learning is specifically designed to be able to handle this, and we will talk about that. So today my agenda is to start introducing what continual learning problem is. In particular, we'll start by catastrophic forgetting, and which is kind of the most well-known issue with continual learning. And then we will talk about the fact that catastrophic forgetting is only one aspect of continual learning, and this problem is really truly multifaceted in nature. And then we talk about some biological inspirations behind the algorithms that we can use in machine learning to perform continual learning. So this part is mainly related to the joint work we did with Risha, and she led our efforts on that. And then I'll talk about two of the recent papers from our group. Paper one is an approach on metaplasticity for overcoming catastrophic forgetting. It's called the slice grammar preservation. And in this paper, we talk about probabilistic distances and how they play a very important role in designing effective regularization-based continual learning approaches. And the second paper is a COLA 2022 paper, a very recent paper that we worked on that combines metaplasticity and neuromodulation approaches to perform continual learning. And then lastly, I conclude my talk with some of the ongoing research thrusts in my lab and some of the current challenges that we are trying to address. So catastrophic forgetting. We said that the distribution of the data constantly changes. For example, we can go from sunny to rainy, summer to winter, and so on, right? Then the question is, can't we just simply keep training the model on the stream of incoming data and expect the model to perform well on all the data? And the answer is no, we can't do that. And if we do that, a phenomena called catastrophic forgetting is going to happen. And I'm going to tell you what we mean by catastrophic forgetting. So we can learn the first task, whether it's sunny or summer, for example, and achieve an acceptable performance. And then when the distribution of the data shifts, and by the way, this shift could be kind of gradual shift or can be sudden. And here we are showing a sudden shift, for example. Then we can keep training the model. The model's performance is going to drop on the new distribution, and we can keep training the model, and the performance becomes better on the new domain. While this costs us a performance drop on the old distribution that we had. Okay, and this is called the catastrophic forgetting problem in continual learning. Here's another example that depicts this visually, right? So assume that we have 4 tasks, and each task is simply a binary classification problem, classes red versus blue, and we are able to train a model to give us the correct decision boundary. Then for task 1, then we fine-tune it on task 2, and it learns the decision boundary for that task and completely forgets what the decision boundary was before. And we keep going, and we see that we are able to learn each task at the cost of completely forgetting what the previous task was. And when we talk about overcoming catastrophic forgetting, we really would like to be able to preserve these decision boundaries that we have found while we are learning the new decision boundaries or extending the boundaries. So we should be able to learn the entire decision boundary in a sequential manner. Okay, and so what is the challenge? The challenge is we don't have access to IID distribution from all our data. We don't want to use data from the previous tasks because that's not scalable. As the number of tasks grows and goes to infinity, we won't be able to carry all the data and fine-tune our models on all the data. So we would like to be able to do this without using previous data. That's the main challenge in continual learning. So here's a fun little example of catastrophic forgetting in a very simple one-dimensional regression problem. This is a project that my undergrad students did to essentially communicate the idea of catastrophic forgetting to their classmates in their class. So we are able to learn and essentially find a regression line using a neural network to the blue points in task 1. And then when we switch and go to task 2, where we are using the green points, we are still able to learn that solve the regression on the new data at the cost of completely forgetting what the previous regression was. So this is a regression extension of the classification problem that we saw. And here we look at the losses. The loss for the first task goes down. And as soon as we learn the second task, the loss goes back up as we see on the left. Okay, but these are very simple examples, one-dimensional, two-dimensional examples. Why should we care about this? It turns out that this problem is generic. We can go and have way more complex situations, and the exact same phenomena happens. So here I'm showing results for some example in semantic segmentation of driving scenes. So what you see in the left is the input, which is it's a synthetic data, but is essentially what would be a driving scene. And we have the ground truth semantic segmentation. And for those of you who are not familiar with semantic segmentation, we assign a label per pixel in this case. So we know that this is road, these are lane marks, cars, and so on. And we have trained the model on a training set and testing it on the test set here, showing that our model performs really well on the test set. So we are able to do this semantic segmentation nicely. But if we change the distribution, so if this is our task 1, sunny, and if we change the distribution to winter, our model doesn't generalize to winter. So we see that it's actually performing very poorly. It sees cars everywhere, and it won't be able to do the semantic segmentation reliably. But if we fine-tune only on the winter data, what will happen is that we are going to forget our performance on the summer data. So catastrophic forgetting is a real issue in one-dimensional, two-dimensional, and n-dimensional problems, regardless of being classification or regression, and we really need to be able to solve this problem. Okay, but catastrophic forgetting is not the only challenge. Overcoming catastrophic forgetting is not the only challenge in continual learning, and this is a multifaceted problem in nature. Why? So let's list what we would like our continual learner to do. So if we had a desiderata, we would like to be able to learn new tasks better than previous tasks. So we would like to not only not forget, but actually learn new tasks more efficiently and maybe faster, maybe with higher accuracy. And that is essentially saying that we would like to have positive transfer from positive forward transfer from previous tasks to the future tasks. We would like to overcome catastrophic forgetting, and that means we would like to have non-negative backward transfer. And ideally, we would like to even have positive backward transfer. And what I mean by that is that if we learn a new task, or performance on previous tasks should be improved as well. So that's positive or non-negative backward transfer. That's desirable. We would like to be able to rapidly adapt to new situation and be able to learn new tasks more efficiently. And from efficient, I mean faster in this case. And then we would like to be able to do all these with constant computational and memory resources. So we don't want to have a situation that's our model, the memory cost of our model grows as we see more and more tasks, for example. So this brings the efficiency point up. And we would also like to be able to perform in a task-free environment. And this is a really challenging scenario where we don't have task boundaries and where we don't have an oracle telling us which task we are solving. We need to be able to infer the task and then be able to solve the task. So that machine learning model needs to be able to do that. And as you can see, we have already itemized 5 points here, and there are actually more things that we can ask from a continual learner, and some very nice recent papers discuss what are the different aspects, how to measure these. And for example, this is an example by Veniat et al. At iClear 2021, where they talk about these different aspects of continual learning. Okay. So
there's a question, Soheil, in
sure.
the chat. I don't know if you can access the chat, but Mark, you can ask the question.
Hi, I'm just thinking by analogy to how people and animals behave. Why can't the machine understand context? Winter and summer are different contexts. Sitting in my math class or my English class are different contexts, and my behavior is different. Trying to pretend that they're the same context makes me forget the rules for one. Why not just make the machine know there are two different contexts with each having its own set of rules?
Fantastic, beautiful question. Thank you so much for bringing that up. So context here could be like, essentially we can say task similarities is a notion of context, right? So if two tasks are similar, I should know that they are coming from the same context. If they're different, if I had a notion of task similarity, I would be able to know whether the context is the same, or this context that I'm currently seeing is similar to something that I have seen in the past or not, right? And then that's one thing. The detection of context itself is certainly a challenge, right? And I'll talk I think the last slide that I have is exactly talking about this detecting context or detecting similarity between tasks is really a challenge, an open challenge in continual learning. And then even if we detect context, knowing what are the shared concepts in different contexts is another challenge. So learning context invariant policies or representations, depending on what type of machine learning we're doing, is also really challenging, right? But that's precisely like a very good point, right? And then the type of continual learning that I'll be talking about today is going to assume that we are not going to add context information. We are going to just simply assume that there is a shift in the distribution of the domain, and that shift in the distribution must be handled by the same function with a single head. So we have one function that has an input, and this input is shifting. So we are in a domain shift continual learning framework, and we should be able to continually accumulate knowledge in this one function that we have, so it can perform in both domains. Does it answer the question?
Absolutely. I think the answer is it's way more complicated.
Right.
Yeah.
Yeah,
I'm thinking that, yeah, mice in a cage learn context, right? If they push the button when the light is green, they get a reward, and if they push the button when the light is red, they get a shock. And so some of this context switching and all that is an interesting part of cognitive psychology and behavior, and maybe there's some insights there.
Absolutely. And I mean, like, we should certainly talk about this offline, because I'm really, really interested in this topic. And, there are certain tasks that context is everything. So essentially, for the exact same domain, you need to behave differently based on the context. And that context information, like how to find that context information, is a really, really challenging but interesting question, right? Yeah. So for the exact same input, we need to behave differently. And if you have one function, it can't be a one-to-many. It's a function by definition, so it can't perform one-to-many. So there is no other way than adding context information and somehow change that function based on the context in those scenarios. But we are not going to be talking about those scenarios, which are a little bit more challenging. Yeah. Okay. So now I'm going to essentially be completely out of my comfort zone, which is machine learning, and talk a little bit about biological inspirations, which is Darisha's expertise, and like mention some of the interesting connections here, right? So how can neuroscience help AI, and specifically help continual learning? So we know that our brains are capable of continual learning. There is a lot of insights in how the brain performs continual learning. There are different mechanisms that the brain uses, and we should really be able to learn lessons from these mechanisms and treat them as biological inspirations to be able to design machine learning algorithms that perform better on, for example, continual learning, right? And then hopefully, eventually, we will get to a place that the machine learning frameworks will be able to help us understand the brain better. So that's, I think, a more challenging direction. Okay, but the key here is, when we say inspirations, we really are not interested in replicating biology. We are just trying to think about it as a functional level. Can we provide a similar functionality? And Demis Hassabis and other co-authors had a very nice paper called Neuroscience-Inspired Artificial Intelligence. And so the summary of that paper is, we should really use these biological inspirations, but not necessarily replicate them for continual learning or achieving other AI tasks. So this is a figure from Darisha's paper, or joint paper with Darisha in Nature Machine Intelligence, that shows some of the key characteristics of continual learning that we talked about, like transfer and adaptation, overcoming catastrophic forgetting, exploiting task similarities or exploiting context, task agnostic learning, and so on. And some of the existing mechanisms in the brain that allow us to achieve these different characteristics of continual learning. Okay, so now just briefly, some biological mechanisms that have analogous ML approaches. Here I'm just mentioning two of them. There are more than two, but one is metaplasticity. And so metaplasticity refers to the morphological and density changes in the dendritic spines that affects neural plasticity of the brain. And it essentially allows us to have heterogeneous plasticity or selective plasticity of neurons. Not all neurons are as selective as plastic as one another, right? But this is like our deep neural networks today are completely different. They, unlike the biological neurons, they actually are uniformly plastic. So if you're training a neural network, each weight of your neural network is as likely to change as each other weight of that neural network. So this idea of having control over plasticity and being able to do selective plasticity has motivated many approaches in continual learning, which we will be talking about shortly. And another one is, for example, complementary learning systems, which is based on the idea of the fast and slow learning between the hippocampus and neocortex. And like we can see analogous approaches in machine learning domain where they use modern like experience replay in, for example, reinforcement learning to mimic something very similar to this fast and slow learning that happens in the brain. So one important point here is that not all machine learning algorithms are inspired by biology, but when we look in hindsight, we see that there are biological mechanisms that are doing something very similar to what we really want at the functional level, to what these approaches in ML are doing. And we should really be able to use insights from biology to design the next generation of machine learning systems. Okay, so so what is the landscape of today's continual machine learning? So there are a lot of papers, right? There are easily like thousands of papers on continual learning that one can find. But if we generally look at the approaches taken by these methods, we see that some of them are changing the dynamics of synaptic weight updates. So how the neural parameters are updated is changed at a very high level. The others are changing the dynamics of neural activations. So this one is on the backward, on the back propagation essentially, and this one is on forward. So we can modulate the forward path to be able to rapidly learn from new tasks, or they dynamically change the architecture. For example, progressive neural networks or progress and compress approaches. So if we look at the continual learning, this is a very like broad categorization of the field. If we look at different methods, we can generally cluster them into replay-based approaches, regularization-based approaches, and parameter isolation approaches, which use these different types of mechanisms that we talked about. And there are many examples of them. For example, regularization-based approaches, elastic weight consolidation is a famous one there, or synaptic intelligence. And there are also other emerging work that are showing the architecture and training regimes are very important for continual learning. For example, if we use an optimizer that prefers flat loss landscapes over sharp ones, that's going to be a better continual learner, right? Or wider neural networks are less prone to forgetting, or dropout and sparsity reduce forgetting, which is essentially different training regimes in the neural networks. Okay, so we know that brain uses a combination of these known mechanisms, and there is not one single mechanism that's allowing us to have continual learning. So really we should, this can serve as a roadmap for designing the next generation of bio-inspired continual learning algorithms. And we know that we need to go towards this having a collection, a set of mechanisms that allow us to eventually have like the ideal continual learning that we really would like to have. Okay, so this slide is a reflection on my previous work in continual learning. And I just sorted all these papers that I had and asked myself what bio-inspired mechanism is used in this paper. And I saw that many of the papers that I have worked on before use only one sort of biological mechanism. And then only very recently we are moving towards like including more mechanisms and having some approach that have multiple mechanisms to solve this problem. And we are seeing significant gains in this. And hopefully in the remainder of the talk, I'm going to talk about two of these papers with you and communicate the ideas. So I'm going to start with a metaplasticity approach called sliced Kramer preservation. This was an iClear 2020 paper, and this was a joint work with Nick Ketz, Andrea Soltaggio, and Praveen Pillai. Praveen and Nick were at HRL Laboratories. I performed this work while I was at HRL Laboratories, and Andrea is at Loughborough University in the UK. So let's look at a very simple problem and essentially revisit the catastrophic forgetting and ask ourselves what mechanisms can be used to overcome this. So here we see a classic toy-like data set called MNIST. This is a handwritten digit recognition problem. And we have task A, which is just solving the MNIST problem, and then task B, which is a permuted version of these digits with a fixed permutation. So as far as the computer is concerned, this is the exact same problem as that. Of course, humans are not very good at understanding these permutations. We are not used to seeing a permuted version of these images, but the machine can figure it out. Okay. So now we have a neural network that sends these inputs, 784 dimensional inputs, that's the dimensionality of MNIST, to a two-dimensional embedding. And then from this two-dimensional embedding, we classify or 10 classes. The reason we are using a two-dimensional embedding is for visualization. Okay. So when we learn task one, we immediately see that here each point represents an image and the colors represent the labels of the image. We immediately see that we have learned a discriminative embedding space. We have different classes sitting near each other, so we are able to classify this problem really nicely. But if you apply send images from task B, of course it gives us garbage, right? Like, because it wasn't trained on task B. So this is not generalizing to task B because it has never seen task B. Okay, now when we go and we train on task B, or performance on task B becomes really good. We are able to essentially have different classes clustered with each other nicely, but this comes at the cost of mixing the distribution of previous problem. So again, catastrophic forgetting. So let's ask ourselves, what do we need here? And what we really need is to be able to learn this new distribution while preserving the previous distribution. Okay, so this is what we would like, we strive for doing. Okay, so how can we do this? And now I'm going to go back in time to 2017 and talk about elastic weight consolidation, a work by DeepMind that addressed this problem the first time. So the idea was that not all synapses or parameters of the network are equally important. So if you have a way of measuring how important the parameters are for task one, maybe when we are learning task two, we are going to not let the network change the important parameters. Okay, so we need to assign importance values to network parameters. And how do we do it? If we are able to find an importance parameter, and I'm going to in the next slide tell you how we can find this, but we are going to regularize the loss for task B with this regularization term that's telling us that the delta, the change in the parameters, should be small for the important parameters. So why is this called elastic weight consolidation? It's because it's related to the idea of elasticity. If a parameter is important, we are going to say it's less elastic. We don't want to be able to change it much. If it is less important, it's more elastic, and we will be able to change it as much as we want. Okay, so that was the idea of EWC, a very famous approach in continual learning. But how do we achieve these, finding these importance parameters? So what we really want is to say we have the distribution of our data in task A, as we saw, and we would like to have a good distribution for task B. So this is achieved by minimizing the loss on task B. But we would like to be sure that after we are updating our model, the distribution of our previous the distribution of our previous data is not changing. So if I send the new data, the new model, if I send the old data through the new model, the distribution should be similar to sending the old data through the old model. Okay, and here I'm measuring that distance between the distributions. Okay, so now you may ask, okay, so here you are using the old data, you are using your probability, the distribution of task A, and essentially you're carrying data around. So this is not continual learning. You're reusing that distribution. Well, we can use a trick here, a two-step trick. First, we can assume that the change in the parameters is small and use a Taylor expansion of our regularization term. And if we do that, we end up having a quadratic term, delta theta transpose omega A of delta theta. And this quadratic term, the delta theta is the change, the omega is the Hessian of our distance. And we now see that what we can do is, after we learn task A, we can simply calculate this Hessian matrix and discard all the data that we have. So we are going to only use this Hessian matrix, and this is going to approximate the loss function, the regularization that we had. So this discards the data, and just in the memory, we have a fixed size Hessian that we have to save. But of course, this is still problematic because the Hessian matrix for deep neural networks can be gigantic. If you have 11 million parameters, this is an 11 million by 11 million dimensional matrix. So then there is another assumption on top of it that we can make and say, we are going to assume that this Hessian matrix is diagonal. Okay, whether is this a good assumption? Not really. And there are a lot of works that show that this is not a good assumption. But if we make this assumption, then we end up having the elastic regularization that we talked about. We see that the diagonal values of this Hessian matrix are exactly the importance parameters that we need to carry. Okay, so now with this, every parameter in our network is going to have a weight and an importance associated with it. Okay, but then the next question we can ask ourselves is, what is a good dissimilarity measure D for these two distributions? And elastic weight consolidation, memory-aware synapses, and a lot of other approaches in the literature, what they do is they look at a sample-based distance. They essentially calculate an expected value of a distance between the output of the current model versus the output of the old model with respect to the same input X. Okay, so this was essentially a very common practice before our work. And then what we observed was this. We can essentially shift the samples around. So if this is our distribution of previous model, this is the distribution of our new model, what we can do is we can shift these samples around and really not change the distribution of the data. But if we shift the samples around and not change the distribution of the data, no catastrophic forgetting is going to happen. Although these methods that use this sample-based distances are actually going to penalize us for shifting samples around. So what I mean is, if I simply shift the samples around, I'm going to get a large regularization for sample-based regularization methods. But if I am looking at a distribution-based regularization, if this is actually a distribution distance like the Wasserstein distance or slice-Kramer distance or max-mean discrepancy, we are going to not penalize our network and have a more flexible regularization. Okay, so while they're both essentially overcoming catastrophic forgetting because the distribution is not changing. Okay, so with this simple trick, with this simple change from sample-based regularization to distribution-based regularization, we devised a slice-Kramer preservation where we are using D to be the slice-Kramer distance. I don't go through the mathematical details of this. The paper, feel free to read the paper and reach out to me if you're interested. But we showed that we are going to significantly outperform the sample-based regularization approach simply using this trick of using distribution-based method versus sample-based regularization. Okay, and now, so here, this is a benchmark problem in continual learning called permuted MNIST. Nobody likes it because it's too simple. So we went to test our algorithm on this semantic segmentation work. And I need to speed up a little bit. We saw that if we simply fine-tune our model on task B, a catastrophic forgetting happens. This is what we observed before. But now we are going to fine-tune on task B while using the SCP regularization, while using our distribution-based regularization. And you see that now our performance is really nice, both on the new task and on the old task. Okay. And then we had some quantitative comparison of this EWC and MAS work as compared to our approach. If we don't do any continual learning, so catastrophic forgetting happens, as we can see down here. But with our approach, we were able to show that we perform much nicer, much better than the sample-based regular.
So, Soheil, one more question.
Sure.
Anura, go ahead.
Hi, Soheil.
Hi.
Thanks for the talk till now. And so I had a question, like in the slide where you were mentioning difference between sample-based and distribution-based regularization, right? So how are we getting the distribution from? Like, is it based on the entire training set, or is it based on like a prior which we have derived?
Fantastic. Yeah, these are empirical distributions. So based on the training sets, right? So based on the, like after we learn task A, we can have a memory buffer of the samples that we have seen on task A, right? Or it can be simply like a large batch, the last batch, if your batch size is large, or the last epoch of training. We approximate the second order Taylor expansion of this distance, assuming that these PAs are the empirical distributions that we have.
Okay, so we can take like a subsample of the data as an exemplar, right?
Absolutely, absolutely. So long as those samples are representative of your distribution. Absolutely.
Yeah.
Okay.
Thank you.
Thank you for the question. Yep. So, and this is a qualitative comparison of our approach with MAS and EWC. Like you can see, they're all doing a fine job finding the road, but you can see in the side of the road, EWC and MAS start seeing after they are trained, they are doing really well. But when we fine tune, they start seeing these weird artifacts, while our approach is essentially preserving its performance much better on this benchmark. Okay, so now this was essentially the distribution-based regularization for overcoming catastrophic forgetting. Now I'm going to quickly switch to sparsity and heterogeneous dropout. And this is the most recent paper that we've worked on. This is a joint work with Vova Braverman at Rice and Hamed Pirsiavash at UC Davis. Okay, and my student Ali, and Parsa is Hamed's student. Okay, so we just saw the regularization-based approaches as one way to overcome catastrophic forgetting. There is another. So what will happen here is that we are essentially calculating the gradient of or loss on task B plus the gradient of regularizer. So we are changing the gradient direction by adding this regularization. So our new gradient is going to be the sum of the gradient of loss plus the gradient of regularizer. Okay, so but the point is, even these regularization-based approaches are changing the way that we are updating our network. So there is a newer class of methods recently proposed to overcome catastrophic forgetting. They're called projection-based approaches. And the idea behind these methods is that let's project the gradient instead of summing it with something else. Let's project it to a subspace. And somehow this projection should avoid interference with prior tasks. So the question is, how do we find this projection? And then to essentially avoid catastrophic forgetting. Okay, and this we are going to particularly be talking about gradient projection memory, and this approach performs really well in practice. Okay, so to be able to understand this, I'm going to very briefly mention the mechanisms. It's actually quite simple. So let's say we have a neural network. We have the activations. So it's just linear, it's a multi-layer perceptron, linear activations followed by nonlinearity, linear, nonlinearity, and so on. And we're actually looking at the activations right here. So activations at the first layer, activations at the second layer. Okay. So, and I'm showing data set A as task A with blue and data set B as task B with red. Okay. So now say we have trained our model on task A. We would like to, and we start training on task B. So now we have the optimal parameters for task A, and we have our parameters for task B. So when we say we don't want any forgetting to happen, we can say that's equivalent to saying that we don't want our activations for our previous data to change based on the change in our parameters. So we would like the activations to be exactly equal to the activations we had before for the old data. Okay. So this means that we can decompose our optimal parameters for task B and say that's essentially the optimal parameters for task A plus some delta W. This is the change of parameters. And then if we calculate, if we expand this further, we see that we have WAX times delta W BXA, and we want this second term to be 0, right? If the second term is 0, it means the activations did not change at all. then, as I said, we need this delta WXA to be 0. So what does that mean? That means that we need to update our model such that it's orthogonal. The updated parameters are orthogonal to all activations of our task A. So if we go and we find a subspace for our activations of task A, and when we calculate the gradient for task B, all we need to do is to project it to the null space of these activations, the activation subspace. Okay, and this is the core idea behind gradient projection memory. It was introduced in Clear 2021 by Soheil et al. Okay, so what are the issues that we can face using gradient projection approaches? First, the activation subspace is assumed to be low rank. Why? Because if it was not low rank, then when we do this projection, we are going to lose all the gradient information. So we would like to have low dimensional or low rank subspaces for our activations. That's one. Second is there is no backward transfer. So this method actually guarantees that our backward transfer is going to be 0, right? Because the activations do not change at all. So we cannot improve on a task that we had learned before, okay? And that's another limitation. So the second limitation has recently been addressed in iClear 2022, and there are other approaches as well that are looking into this. For example, the trust region gradient projection for continual learning by Lin et al. Address that. But we focus on the first issue, that how can we ensure that we have low rank activations, low rank neural activations. Here again, biology comes to our help. We know that sparsity is a fundamental computational principle in neuroscience, right? And when we say sparsity in biology, we're talking about, in biological neural networks, we're talking about different types of sparsity, from synaptic weights to activations to the lifetime sparsity of a single neuron, right? So we actually have been in contact with folks at Numenta, Sabutai, and his team, and they have been developing very, very exciting tools in deep learning that enforce this sparsity with sparse activations through k-winners. So you essentially, your nonlinear activation is just going to pick the top k activations and zero out everything else. So that's the sparsity in activations. And they have worked also on sparsity in synapses, but we're going to focus on sparsity in activations. So we showed in our work that sparsity in activation actually leads to low-rank activation subspaces. I should emphasize that this is not theoretically guaranteed to happen. In fact, one can show that sparsity should not result in low-rank activations, should not necessarily result in low-rank activations. But in practice, when we apply these sparse activations, we see that on a lot of different data sets, the activations become low rank. And also we showed that lifetime sparsity, and I'll mention what this is, boosts continual learning. But let's start with the first one. So if we simply train a neural network on the MNIST data set, for example, and if we use ReLU as our activations versus the k-winner activations, these k-winner activations are sparse activations, and we measure the rank of our activations. And in fact, we can look at the captured variance as a function of number of eigenvectors as a proxy for rank. We see that, so at 100%, we are actually looking at the rank. We see that adding sparsity, so orange is ReLU, blue and red are sparse version activations with different levels of sparsity. Red is more sparse, blue is less sparse, and orange is just ReLU, which is dense. We see that the rank goes up as we use the dense, and it goes down as we are using the sparse activations. And this is true for layer 1 and layer 2. So in fact, sparsity is going to reduce the activation, the rank of the neural activations. And second, we use the idea of lifetime sparsity, which means if a neuron has been activated recently, it shouldn't be activated again. And based on this idea, we devised this new dropout algorithm that's, we call it heterogeneous dropout, as opposed to vanilla dropout that drops each neuron activation with just a fixed probability. We actually track the frequency of activation of each neuron, and then based on that define the probability of dropout. And now we have a dropout that's heterogeneously applied to our neurons, right? And it's essentially enforcing a neuron that's been frequently activated to be less activated now. So it's related to the idea of a lifetime sparsity as well as the idea of neuromodulation, because we're down modulating the activation of a neuron in this case. And so we saw that this simple heterogeneous dropout technique will lead to non-overlapping neural activations. And we show that it's actually going to help us to perform continual learning. So now we combined this idea of a sparsity in activations, a sparsity of lifetime, as well as gradient projection memory, and came up with this new architecture that uses GPM with a sparse model. And we show that if we design a task with here 50 binary classification, this is just simply a visualization, where the different tasks are shown with different colors. And we start learning the first task and then go and learn more and more tasks, as you can see it in the bottom. So what will happen is that the proposed sparse GPM will actually keep continually learn the tasks, while the GPM by itself, it learns the few tasks really well, but immediately starts not behaving very well because the low rank assumption is going to be violated, that it won't be able to learn the new tasks efficiently. So this was very exciting to be able to use the sparsity of biological neurons in a deep learning approach. So I'm going to quickly wrap up. So here we show the performance of this sparsity plus GPM approach on various benchmark data sets. If you're interested, please look at the paper. And for the sake of time, I'm going to just skip the results that we have. And the results are all included in the paper. And we show that continually this sparsity plus heterogeneous dropout help boost continual learning algorithms. Okay, the last 3 slides that I have are going to be about the current thrusts in my lab. We are part of the Shell DARPA program, which is the Shared Experience Lifelong Learning. And so the idea is now we worked a lot on continual learning for one agent. What will happen if we make multiple agents and let these agents communicate with each other? Okay, how fast can we learn? What are the challenges that we're going to have when we have multiple lifelong learning agents? Of course, like an immediate result would be like we are going to be able to learn the entire tasks faster. Okay, but so this is some of our recent results on a 100 task benchmark. So the blue curve shows the single lifelong learning agents. I mean, it's overcoming catastrophic forgetting. It starts learning from the first task, and it eventually learns all the tasks with very high accuracy. The orange line shows the multitask learner. So if we do joint training on all the tasks, and the red and green show when we have 10 agents and when we have 5 agents communicating with each other and learning. These are lifelong learning agents that are communicating with each other and learning the tasks. And we can immediately see that we're getting closer and closer to the multitask learning. And we can learn the tasks significantly faster than a single agent. So here, some challenges are what to communicate, when to communicate, and how to integrate the information between different agents. So that's one of the recent thrusts that we are working on. Another thrust that we're currently working on is going beyond supervised lifelong learning, and we are working on continual self-supervised learning of invariant representations in neural networks. And we actually have this paper that's just got published on arXiv that shows that multitask learning or joint training is not necessarily an upper bound for continual learning. Specifically, if you are using continual self-supervised learning, we show that continual learning often provides better performance compared to multitask learning. Okay, I don't want to go too much through the details of this, but the main belief that multitask learning is an upper bound for continual learning is not necessarily true. And can discuss if you're interested about that. And lastly, and going back to the question of context, we are actually working on finding task similarities. And this is another paper that recently was posted on arXiv from our group. We use a task, we devise a computationally efficient task to vector embedding. And we show that the distance between our embedding or embedded tasks is actually a very good indicator of forward and backward transfer on multiple different benchmark data sets in continual learning, including the NIST dataset, split CFAR, and split tiny ImageNet. So this is another very exciting area that gets us closer and closer to using context, to be able to use context for continual learning. And to summarize, so we talk about continual learning being a multifaceted problem. We talked about some of the biological inspirations that are very important in designing next generation approaches for continual learning. We looked at novel distribution distances to use as regularization-based approaches for continual learning. And lastly, we saw sparsity and its role in continual learning. And so we briefly also mentioned some of the core challenges in continual learning, like going toward multi-agent and self-supervised continual learning. And we didn't get a chance to talk about embodied continual learning, which is a very interesting topic by itself, but maybe another time. Okay, and I wanted to just thank my students and my collaborators and acknowledge DARPA's funding for the research that I just talked about. Yeah, with that, conclude my talk. Thank you. I would be happy to take any questions.
Thank you, Soheil. I think we have a question already from Fatima in the chat.
Yeah.
Fatima, you want to ask?
Sure. Dr. Kolouri, thank you for the wonderful talk. I just had a question about your dropout method that you mentioned. So is it like during one task, the dropout module is basically tracking which neurons are more active, and then in the next task, it's limiting their participation, basically.
Right.
Those neurons out.
That's absolutely accurate, right? So what we do, it's, I think, shown here in this slide. So what we do is we keep track of the activations in these BTLs are exactly doing that, right? So during learning a task, we keep track of the frequency of activations. And after that task is done, we go and we update the probability of dropout based on the frequency of activations.
Okay, I was just wondering, because if we in this process, it may be so that as the tasks progress, as we encounter more and more tasks, more of the neurons can, stop from participating in learning. So can that affect the learning capabilities of the network?
Fantastic question, right? So essentially, the core thing that, if I understand it correctly, the core question that you're asking is these frequencies can change depending on which phase of training you are. In early stages, they can be very different than in later stages. And so we can, we have devised different approaches for this. Like in one approach, we simply just look at the last epoch, right? But you can think about a moving average like frequency, right? That you rely on the latest frequencies that you're calculating. If you have an epoch, right? You're learning in an epoch settings, right? You have these frequencies per epoch, and you average them based on like adding more weight to the most recent epoch and then less and less weight to the previous ones, right? And with that, you will kind of get rid of this change of frequencies through the phase, and you rely on the latest, the activations of your latest model for a task.
Thank you. I also had another question, which is not related to this one, but an earlier slide you had mentioned that wider networks tend to have less catastrophic forgetting.
Right.
I was wondering if you could please elaborate on that a little.
Yes.
A little, like what's the intuition behind it?
Yeah. So these are the works by DeepMind, actually a friend of mine who is no longer at DeepMind. But in any case, so if you search, the DeepMind group had many publications on this different training regimes. And so these two are actually very much related. The first two bullet items are very much related. So we said in the first bullet item, we say the optimal with flat loss landscape leads to less forgetting. That's kind of intuitive, right? So what we mean is that if we change our parameters with the delta theta, that delta theta is not going to change the loss
as much, yeah.
Right? So your loss is going to be low. So that's very intuitive why we would like flat loss landscapes. And then these wider networks, there are recent papers that are showing that wider networks lead to more flat loss landscapes. Okay. And there are connections with neural tangent kernels as well. That's what's used for proving anything for these wider networks. But the idea is very similar. The wider your network is, you can show that the loss landscape is going to behave nicer. Similar with residual connections. If you use residual connections, you will end up having smoother loss landscapes, right? These are all related to each other. Dropout is a little different story. Dropout affects the sparsity of activations, which is related to the sparsity part of the talk.
Yeah, thank you so much.
Absolutely.
As we are on the sparsity and dropout question, I think there are some studies that are showing that if you incorporate sparsity in your model, the classes that are underrepresented or data points that are more on the tails are not probably benefiting. It could be actually worse for them. So did you do any ablation studies on that?
So fantastic question, Darisha. Thank you. Yes, so you're absolutely right? So sparsity is performing is essentially behaving as a regularization, right? And those points, the outliers or the few points that we have are behaving like noise as far as the model is concerned, right? We don't have a lot of data there. And this regularization is going to treat them as noise, essentially, right? So it's not really good for the situation where we have underrepresented samples from a distribution. But that said, we haven't done any rigorous studies on that. So it's a really interesting point, though.
Thank you. Other questions for Dr. Kolouri?
I have a question.
Please go ahead.
Thank you, Soheil. Very interesting topic, very exciting methods that you presented here. You talked about the methods that includes regularization and modifications to some of the architecture and training strategies. And in the end, you talked about the context detection and measuring the task similarities,
right,
which made me think of the uncertainty estimation tools that we use for detecting out of distribution in the data. And that comes to the data. And I have seen a lot of online learning and continual learning that uses that.
right.
I wanted to know your opinion. What do you think of using out of distribution for online learning and how it can combine with these techniques that you mentioned about regularization and the architecture of the model?
Beautiful. Thank you. This is a fantastic question. Thank you, Nima. So some little detail that was kind of brushed under the rug here is we are solving these different tasks. So you can see I'm highlighting different tasks with different colors, for example, here, like task 1, task 2, task 3, and so on, right? And this consolidation that we are talking about, this calculation of the Hessian matrix or approximating its diagonal value, is usually done at the task boundary. Okay, so we are assuming that the task boundary is known. We know when we are seeing something new, right? And so this assumption is a little bit problematic, right? Like, how do you know that you're seeing something new? And what you are talking about, this out of distribution detection, is actually a way to for us to be able to automatically detect a change in task. And now we are at the task, essentially detect the task boundary. And after we detect the task boundary, we can do all this consolidation, calculation of the importance parameters and all that before we start learning the new task. So they're very much related. And like the task similarity, I would say, would go one step further, because out of distribution detection will only tell you whether this is new or not, whether this is something that you have seen or not. But if you are able to do task similarity, you can say, yes, this is new, and it's mostly similar or is closely related to task X that I have seen in the past, and least relevant to task Z that I have seen in the task in the past. So that's a very powerful powerful tool to integrate into all continual learning algorithms. I hope that answers your question.
That's it. So you're essentially saying that task similarity is a better alternative for out of detection.
Not necessarily better alternative. I'm saying that it's the task. If you're able to measure the similarity of the task, you already have a built-in out of distribution detection.
I see. Right. I see. Yeah, thank you.
Of course. Yep.
Thank you so much, Soheil, for taking time and sharing fascinating results on lifelong learning and how you're advancing to multi-agents. I look forward to learning more about your research in the coming days and years. But if you have further questions for Dr. Kolouri, please feel free to reach out to him. He is quite responsive. So um, that's it for today's session. Thank you, Soheil.
Thank you, Darisha. I really appreciate the opportunity. Yep.
Yeah. Bye.
Bye. Bye, everyone.